Alrighty. Hello, pre-calculus students. Today is October 31. Happy Halloween. You should, however, be watching this on or around November 6th. So that's the Monday that I'll be canceling class because I'll be out of state. So I'll be recording a lecture today for that. So in the context, right now we've just finished talking about inverse sine and inverse cosine, with the idea being that, all right, if you want to find an inverse to cosine, it's automatically a little bit silly to try to do that, because the graph of cosine looks something like this. It's not one-to-one. So you can't actually get an inverse to it, so what do you do instead? You say, well, I'm going to take as much of it as I can while still being one-to-one. And there you go. If you only see that much, that red bit, this is, however, one-to-one. It has an inverse function. Inverse cosine is the inverse to that little red stretch. So that just means it records the angle, whose cosine is x, which happens to live between 0 and pi. Alright, but with that refresher out of the way, let's try to do the same thing for tangent. So let's start by graphing tangent. So you might remember tangent over 0 is 0. It's got a vertical asymptote at pi over 2, which makes sense because pi over 2 corresponds to a vertical line. It's got a vertical asymptote at negative pi over 2, and then it repeats. All right, so you look at this for a second. Is it one-to-one? No. Right, it fails the horizontal line test. There's a horizontal line, it crosses this graph infinitely many times. But can you restrict the domain a little bit to get something that is one-to-one? And the answer is obviously yes, otherwise why would I ask? If you only saw that little green bit, well, that's of course one-to-one. There's the thing that I'll invert to get inverse tangent. Definition 7.2.1, the arctangent function, denoted arctan of x sometimes inverse tangent of x, is the inverse to tangent of x after its domain has been restricted to, let's see, negative pi over 2 to pi over 2. You can't include the endpoints because, well, there are vertical asymptotes there. The endpoints aren't in the domain of the whole function. So the graph of the inverse is then given by taking that green piece and flipping over the line y equals x, so swapping x and y coordinates. So that intercept is still at 0, 0. It goes up. And, well, tangent seems to have a vertical asymptote of pi over 2. So this will have a horizontal asymptote at y equals pi over 2. Then it'll have another horizontal asymptote, also at y equals pi over 2. Done. There's the graph. Let's check its domain. So remember how to check the domain. You just need to know what x values appear on the graph. And, well, yeah, it sure looks like all of them do. And let's do a sanity check. That should be the same as the range of this. Yeah, all output values are achieved by tangent. What's its range? Well, it looks like it doesn't quite make it to pi over 2. It doesn't quite make it to negative pi over 2. Cool, with open parentheses. All right, so let's recall the following. So, let's start with inverse cosine because I drew that picture at the top of the page. So, inverse cosine, its range is same as the domain of this function. And the red function has domain 0 to pi. And so inverse cosine has range 0 to pi. And it has domain. Well, its domain is the same as the range of cosine. Range of cosine is -1 to 1. Inverse sine, okay, let's maybe recall just by sketching the graph. Inverse sine also not 1 to 1. And if you want it to be 1 to 1, it looks like there's the amount of it you want. Inverse sine has range -pi/2 to pi/2. And domain, -1 to 1. Inverse tangent, well, we just drew that. It has range -pi/2 to pi/2. And domain, -∞ to infinity. All right, so today's going to be all about thinking about how to compute certain things involving inverse trig functions. Let's start by even just thinking about like what these inverse trig functions mean. So if you want the inverse sine of 6/7, let's go over here because I'm going to do something else down here. So let's think about what that is. Sine inverse of 6/7. So inverse sine takes a ratio and produces an angle. Is the angle with, I can spell out the word with sine of theta equal to 6/7, and which sits in -pi/2 to pi/2. All right, so let's see, it certainly can't be negative because sine of, 6/7 is like there-ish on this graph upstairs. So inverse sine of 6/7 is going to be between 0 and pi/2. Let's draw a picture of what that means. So sine theta, well, that's opposite over hypotenuse. So that means I could draw a picture of this. That'll be 6/7. So the opposite side length 6. Hypotenuse has length 7. There's the angle theta. This is sine inverse of 6/7. Cool. Let's play something similar here. Let's try to compute inverse tangent of the log of 0.235. And again, we'll draw a picture. And you know what I'm going to do? ln of 0.235 isn't going to be a reasonable number. ln of 0.235 is somewhere around -1.44. So, all right. So it's inverse tangent of a negative. So that means that this angle, oh, you couldn't see what I just drew. So this number, -1.44, is negative. So I want tangent to be negative. Oh, I guess if I want to draw the horizontal line, I'll need to draw it here. So I want like that angle. Or alternately, -1.44 is like here-ish. So there's inverse tangent of -1.44. It'll be negative. It's also in between -pi/2 and pi/2. So this is in quadrant 4 and has tangent of theta about -1.44. So let's draw a picture of this angle. So it's in quadrant 4, and its tangent is -1.44. That means that its slope, its rise over 1, is -1.44. There's a picture of this angle. All right, cool. So let's carry on. This idea of drawing triangles we'll use an awful lot on later pages of this set of notes. Let's remember this first. Sine of the inverse sine of x. Let's remember what inverse sine of x means. Inverse sine of x is, quote unquote, the angle whose sine is x. And maybe we can be explicit. This is the angle in negative pi over 2 to pi over 2 with sine theta equals x. Oh, so what does this say? This is saying this is an angle whose sine is x. What's the sine of this angle? Well, I just told you the sine is x. Similarly, cosine of cosine inverse of x is always x. Tangent of tangent inverse of x is always x. Where always is a bit of a stretch. It has to be on the appropriate domain. This number x needs to be in the domain of inverse sine. This x needs to be in the domain of inverse cosine. This x needs to be in the domain of inverse tangent. Oh, everything's in the domain of inverse tangent. There's no domain constraint there. Groovy. So, let's carry on. Here's the goal that I want to do today. So, somehow most of what I just did should have felt kind of review-ish, except for actually getting this graph. But even that should have felt pretty familiar. I want to get a formula for what the sine of the inverse cosine is and the cosine of the inverse sine is. And before I get that formula, let's go ahead and pull up a Desmos graph. I'll encourage you to pause the video right now and pull up a Desmos graph. Good, you've done that. Let's graph these. Sine of arc cosine of x. Oh, that's interesting. It's like a semicircle. How about cosine of arc sine of x? Oh, weird. That's also a semicircle. So that's interesting. It looks like these both are the same functions, according to this graph. That's surprising. Let's see what that function is. And in fact, the ideas that we'll use to do this will let you do anything in the form trig function evaluated at inverse trig function. So suppose I wanted you instead to sketch the graph of sine of inverse tangent of x. You could. You could figure out exactly what this curve is. All right. Let's do that then. So, as we fill in and get the formulas that go here, I'll flip back to this page and we'll fill them in together. All right, so let's begin with this. Let's try to compute the cosine of the inverse sine of negative 3 over 5. So let's remember what this means. So let's let theta be inverse sine of 3 over 5. So I'm thinking of this thing that is inverse sine of 3 over 5. I'll call that theta. And I should think of it as an angle. Inverse trig functions take ratios and give you angles. Right, because that's what a trig function expects as its argument. So inverse trig functions produce that angle. So let's let theta be inverse sine of negative 3 over 5. Then, well, let's think about what that means. That means that theta is in between negative pi over 2 and pi over 2 and sine theta is equal to negative 3 over 5. So let's remember what all that means. The fact that it's between negative pi over 2 and pi over 2 means it has to be in this range. I know that sine is negative 3 over 5. Well, sine is positive here, it's negative down here, so this angle's down here. There's this angle theta. Excuse me. So theta is an angle in quadrant 4, and sine of theta is negative 3 over 5. So what's the story here? So all I need now is to compute cosine of theta, because I want the cosine of the inverse sine of 3/5. So I just need to compute cosine of this angle. Let's use this triangle to compute that. So here's a triangle. This angle is theta. It's in quadrant 4, so this is a correct picture. Sine is equal to opposite over hypotenuse. So the opposite side, I'll label it as -30. It's negative because it's pointing down. And this hypotenuse has length 5. I guess that means the adjacent side length. Well, we could solve to find it. Or you could say, well, you recognize this. This is a 3, 4, 5 triangle. Oh, wait, that tells you everything, right? You can now compute cosine of theta is equal to opposite over hypotenuse. That's 4 over 5. So that means that the cosine of the sine inverse of 3 over 5 is 4 over 5, -3 over 5. And let's check that by, again, looking at this Desmos graph. There's the cosine of the inverse sine of x. Let's zoom in a little bit. I want to plug in x equals -3 over 5. There's line at x equals -3 over 5. Yeah, that y value looks like it's 4 fifths. It's 0.8. Graph checks out. Cool. Let's do something similar. Let's compute. Oh, well, that is that. Okay. So cosine of inverse sine of 3/5 is equal to the cosine of this angle theta is 4 over 5, adjacent over hypotenuse. Groovy. Let's do this in general. Let's get a general formula for cosine of the inverse sine of x. So let's do exactly that. Let's let theta be inverse sine of x. Then sine of theta is x. And theta is in quadrant 1 or quadrant 4 because of this picture. The range of inverse sine is quadrant 1 and quadrant 4. And we'll do this 2 different ways. We'll do this by using the Pythagorean identity, so we'll use sine squared plus cosine squared equals 1. Or we'll look at a right triangle. And the right triangle thing is what we just did, so maybe I'll do that again while it's fresh. So I know that sine of theta is equal to x. And there's something slightly dishonest about this picture. So let's draw this angle theta. Sine of theta is opposite over hypotenuse, so I'll write that as a fraction. It's x over 1. Opposite x, hypotenuse 1. And let's call that adjacent to avoid confusing myself with variable names. So let's compute the adjacent side length. X squared, let's compute the adjacent side length. So x squared plus adjacent squared is equal to 1 squared. 1 squared is 1. Solve this for adjacent. So I guess I need to subtract x squared to the other side. Adjacent squared equals 1 minus x squared. Get rid of the square with the square root. Adjacent equals plus or minus the square root of 1 minus x squared. And let's think about this plus or minus. So we kind of saw in this example that negative numbers can mean something here. A negative would just mean that like this points to this direction instead of that direction. But remember, this sucker is in quadrant 1 or quadrant 4. Both of those have positive x value, so this should point to the right. So this will be plus. All right, I've computed the adjacent side length is plus the square root of 1 minus x squared. So that means that cosine of sine inverse of x, remember this is the thing that's the angle theta, is equal to cosine of theta, is equal to adjacent square root 1 minus x squared over 1, also known as just square root of 1 minus x squared. So there it is by drawing a triangle. Let's also use the Pythagorean identity. So here's what I know. I know that theta is in quadrant 1 or quadrant 4. I know sine of theta is equal to this number x. I would like to compute cosine of theta. And there's the general way to do that. I know that sine squared theta plus cosine squared theta is always equal to 1. Well, sine of theta is x, so that'll give me x squared plus cosine squared theta is equal to 1. Solve for cosine squared. Cosine squared theta equals 1 minus x squared. Get cosine on its own. Cosine theta is plus or minus square root of 1 minus x squared. And now let's use this. This angle theta is in quadrant 1 or quadrant 4. That was a bad cue. Let's draw a picture of that. So that's this region. Oh yeah, cosine is positive in that region. So cosine of theta is plus the square root of 1 minus x squared, which is what we got the previous time. So let's flip back to the previous page. Put that formula in. Cosine of the inverse sine of x is always the square root of 1 minus x squared. And let's check that using the Desmos. Square root of 1 minus x squared. Parentheses matter, even though Desmos seems to not think so. Yeah, that looks pretty good. It's the same semicircle. So there's something really cool about this. This is a very geometric object. It's what's the x value, what's the cosine, if you know the y value. Sine is the y value. So this is saying if you know sine, how do you get cosine? You can use this algebraic formula. So this algebraic formula captures some trigonometry, some geometry. All right, so let's do the same thing again. And in fact, before I do it, I'll give you some encouragement here. Pause this video here. Complete, or at least make an attempt to complete, this next example. No. Complete this example right here, bottom of the page. And then if you're feeling ambitious, finish out the section of notes. Compute this. And then we'll advertise the extra credit. Maybe I'll even draw a picture for those who want to stick around till the end. So let's compute the sine of the inverse cosine of 5/14. And the procedure is going to be the exact same. And again, you've already done this. So either you use the Pythagorean identity or a right triangle. If this were a normal time, I would ask you which one you would like to do. But I guess, well, we did the right triangle thing twice. We did the Pythagorean identity only once. Let's do the Pythagorean identity. So let's follow this strategy. So this angle theta is inverse cosine of 5/14. That means cosine of theta, 5/14, is 5/14. And let's add something else. And theta is in the range of cosine inverse, which is 0 to pi, or if you want to say it in yet another way, quadrant 1 or quadrant 2. So let's use that to now compute sine of theta. So what do I know? I know sine squared theta plus cosine squared theta is equal to 1. I'll be a little bit lazy. I'll let s equal sine theta so I don't have to write sine theta so many times. Sine squared plus, I know what cosine is. It's 5/14. 5/14 squared equals 1. All right, so it looks like this number is like slightly more annoying, but it'll actually work out okay. S squared is equal to 1 minus 5 squared is 25. 14 squared, I believe, is 169, but I'm not going to do that multiplication on my own. I'm not going to trust myself to have done it correctly. 169. So I've subtracted this to the other side, and I've evaluated it. So let's carry on. S squared is then equal to, well, I need to get a common denominator. 169 minus 25 over 169. 9 minus 5 is 4, 6 minus 2 is 4, 144 over 169. So it sure looks like s squared is plus or minus the square root of 144 over 169. And you should always be like a little bit cautious whenever you just write a square root. You should try to check for any, well, one, there's like a denominator in this fraction. There's a fraction under the square root, so you should like do something about that. Let's also check this and see if there are any perfect square factors. Because there's one that I know I have. That 169 came from 13 squared, so I know 169 is 13 squared. That's squared. Oh, I should deal with the plus or minus at some point also. Plus or minus square root 144 over 13, because 13 squared is 169. How about that 144? You might recognize what that is as a perfect square, but even if you don't, you have access to a machine. Square root of 144 is 12. So apparently s, oh, nope, I undid the square by taking the square root. The squares should go away. S is equal to plus or minus 12 over 13. Let's deal with the plus or minus. It can only be one or the other. Theta is in the range of inverse cosine. That's quadrant 1 or quadrant 2. Oh, quadrant 1 or quadrant 2. I guess it in fact has to be quadrant 1 because cosine is positive 5 over 13. In quadrant 1, sine is positive 12 over 13. So the sine of the inverse cosine of 5 over 13 is 12 over 13. And you know what? Let's again check this by appealing to Desmos. This time I'm interested in sine of arc cosine. X equals 5 over 13. So I see some output value there. Maybe I don't recognize whether or not that's 12 over 13. Well, 23, 13. Oh yeah, so that's the right X and Y value. Cool. I guess you could also take a calculator and ask it to evaluate a sine of inverse cosine of 5/14, but I wanted to use a graph this time. Excellent. So we can compute sine of inverse cosine of a fraction using exactly the same procedure. Let's compute sine of the inverse cosine of x for any x. And maybe you even have a pretty good idea what this will be. Based on the fact that it should be the same as cosine inverse of sine of x. But let's go through the motions. Let's let theta be inverse cosine of x. Then cosine of theta is equal to x. I want to compute sine of theta. I guess I just did an example using the Pythagorean identity, so this time I'll use a right triangle. So let's draw this right triangle. I have an angle, theta, and its cosine is x. So that picture just came from cosine of theta equals x. Let's label that opposite side with something. Let's compute that opposite side length. So, since this is a right triangle, I better have x squared plus the opposite side length squared equals 1. Solve for opposite side length. In fact, this looks pretty familiar, right? We'll get opposite squared equals 1 minus x squared. Opposite appears to be square root 1 minus x squared. Maybe we'll worry about the plus or minus. So remember, this angle theta, it's in quadrant 1 or quadrant 2, because that's the range of inverse cosine. The sine, or I guess this opposite side length, will always be positive in that range. So if that thing is positive, the opposite side length is square root of 1 minus x squared, so sine of this angle is square root 1 minus x squared over 1. Oh, so it's just the square root of 1 minus x squared. Flip back to page 1. we now have formulas for the sine of the inverse cosine of x and the cosine of the inverse sine of x. Let's try to play a game like this. Same game. But let's try to compute cosine of the inverse tangent of an angle. So, I think I might even do this two different ways. So, there's space here to use a right triangle to do it. So let's think of this angle theta. Let's think of inverse tangent of 4 fifths as an angle, because it is an angle. It is the angle whose tangent is 4 fifths. Tangent of theta is the tangent of tangent inverse of 4 fifths. Negative 4 fifths is equal to negative 4 over 5. And let's figure out what quadrant this angle is in. So theta is in the range of tangent inverse. And in case you need a reminder, let's flip back and see the range of inverse tangent. The inverse tangent, its domain is negative infinity to infinity. Its range is negative pi over 2 to pi over 2. So in terms of angles, that's like that much. That's quadrant 1 or quadrant 4. Okay, so let's deal with that. So here's the picture that we'll draw. Well, I guess the tangent is negative, so I know it's in fact in quadrant 4. So now that I have that, let's draw a picture. There are my coordinate axes. Here's my tangent. There's the angle theta. I know the tangent of theta is negative 4 over 5. So negative 4 is the opposite, adjacent is 5. Let's compute the hypotenuse. Hypotenuse, so the square of that will be 5 squared plus negative 4 squared. But it's getting squared anyway, so who cares about that negative sign? Is equal to 25 plus 16. I believe that is 41, although with no students here to double check me, maybe I should try to be confident. 5 plus 6 is 11. Carry the 1. 2 plus 1 is 3. Plus 1 is 4. Yeah. So that means the hypotenuse is the square root of 41. And it's a hypotenuse, so there's no need to worry about whether it's positive or negative. So it sure looks like then cosine of theta, the thing I want to compute, is equal to adjacent 5 over hypotenuse, square root of 41. And that's got a square root in the denominator, so let's get that square root out of the denominator. Let's multiply and divide by square root of 41. So cosine of the inverse tangent of negative 4 over 5 is 5 root 41 all over 41. And you know what? Let's check that resorting to a machine. And I'll use this machine this time. So let's compute the cosine of the arctangent of negative 4 over 5. All right, about 0.78. Let's also compute, my memory is like a goldfish, so 5 times square root of 41, close parentheses, divided by 41 is 0.78. Yep, they're the same. So, calculator check has walked out. Groovy. So, you can use the same idea whenever I ask you to compute any trig function of an inverse trig function. Inverse trig function of a number tells you that this is an angle whose whatever trig function I've told you has some value. You can then maybe draw a right triangle, say something about this angle, find the missing side on that right triangle. Once you know that missing side, you can figure out the trig function that you're interested in. If you want to do this for cosine of inverse tangent, oh, there's all kinds of typos. You want the cosine of inverse tangent of x and the sine of inverse tangent of x. You want both of those in this section. Let's let theta be the inverse tangent of x. You need to discover cosine of theta and sine of theta. So you do know one trig function of theta. Tangent of theta is the tangent of the inverse tangent of x, is x. You now want the cosine of the inverse tangent of x, which is just the cosine of theta, because this theta is tangent inverse of x. You also want the sine of the inverse tangent of x, which is the sine of theta, because theta is the inverse tangent of x. You'll need to be careful with negative signs. To be careful with negative signs, think about quadrants. So let's translate this just a little bit, and then you'll report this as an extra credit to me at some point. So I know that tangent of theta is equal to x, and theta is in quadrant 1 or quadrant 4. Because that's the range of inverse tangent. Use that information drawing some right triangles. Figure out cosine and sine. All right, excellent. So, do I go on after this? No, I think I stop here. I hope this has been a reasonably pleasant lecture. I'll see you all on Wednesday if you're watching this on time. Otherwise, whenever it is I see you next. Ciao.